for anyone out there, trying to make sense of number theory, the OEIS, right, the Online Encyclopedia of Integer Sequences, it's an incredible tool.
Yeah, it's really more than just a catalog of numbers.
Yeah.
It's really like a roadmap for mathematical ideas,
Right, and you start to see all these connections that are maybe hidden at first.
Exactly,
Yeah.
exactly.
So,
especially for students, this is like a Rosetta Stone almost
Yeah.
for these sequences, and you can see these patterns that seem completely unrelated,
right.
but then suddenly you realize they have a common mathematical origin.
Yeah, and so that's what we're going to do today, right? We're gonna dive into one of these sequences. It's A000188.
Okay.
And what's really interesting about this one is that it has these multiple definitions,
Uh-huh.
and they all seem kind of different right off the bat.
Okay.
One way to describe it is as the number of solutions to the congruence x squared congruent to 0 modulo n. But then you can also say that it's the square root of the largest square that divides n.
Uh-huh.
And then there's this third way, which is the maximum value of the greatest common divisor of d and n divided by d, where d is any divisor of n.
Right.
And what's so cool is that, those three things sound completely different,
They do.
but they all describe the exact same sequence.
And that's the real aha moment here, right?
Right.
Is that these different ways of thinking about a number, whether it's through this modular arithmetic or its square factors or the relationships between its divisors, they all lead to the same sequence.
It's all the exact sequence.
And it wasn't obvious, it took really sharp mathematicians like Lebos Elmer
right.
and Henry Bottomley to actually
to prove it.
To prove it, yeah.
And it really kind of gets to this really fundamental principle in mathematics, right? That you can have these different perspectives that can all converge on the same truth.
Absolutely. It's about connections and seeing how things are related.
Yeah, and that's what makes it so exciting, I think.
Yeah.
So let's start with the definition that maybe feels the most concrete, right? The square root of the largest square dividing n.
Okay.
And the OEIS gives some good examples to illustrate this.
Yeah.
So for like n equals 8, we see that a of 8 is 2.
Right.
So why is that?
So if we look at the factors of 8,
Mm.
which are 1, 2, 4, and 8,
Mm-hmm.
the biggest one, the largest one that's a perfect square,
Yeah.
is 4.
Okay.
And then the square root of 4, of course, is 2.
Right.
So that's why a of 8 is 2.
Makes sense. Okay.
Yeah.
Another one is a 9 that's equal to 3.
Okay.
And that one seems even more straightforward.
Yeah, 9 itself is already a perfect square.
Right.
So the largest square dividing 9 is 9,
Uh-huh.
and the square root of 9 is 3.
Perfect. Okay.
So it fits.
Now a of 10 is 1.
Okay.
And this one, when I first saw it, I was like, wait a minute, what's
Yeah.
going on here?
Yeah, 10 is what we call a square-free number, meaning that the only perfect square that divides it is 1.
Right.
And, of course, the square root of 1 is 1.
Is 1.
So a 10 equals 1.
It fits.
It fits. And the OEIS makes a point of this, right?
Yeah.
That for any square-free number, the value of the sequence is going to be 1.
Okay.
So essentially, it doesn't have an inner square root.
Right.
That's bigger than 1.
Okay, so we have these examples, right?
Yeah.
But how does that relate to that first definition we talked about, the number of solutions to x squared is congruent to 0 modulo n?
Right.
I mean, it seems like we're talking about totally different math here, right?
Yeah, this is where number theory just kind of shows its beauty.
Okay.
Let's go back to n equals 8.
Okay.
Right, so we're trying to figure out how many values of x, when you square them, you get a remainder of 0 when you divide by 8.
Yeah.
So if you go through all the possible remainders when you divide by 8,
Right.
0, 1, 2, 3, 4, 5, 6, 7,
Yeah.
you find that, okay, 0 squared, that's 0 modulo 8, and then 4 squared is 16,
Yeah.
which is also modulo 8,
Right. Okay.
and no other remainders will work.
Right.
So you have these two solutions, x equals 0 and x equals 4,
Yeah.
modulo 8, and that matches perfectly with what we saw before,
Yeah.
where a port of 8 was 2.
Right.
So it's amazing how a question about these solutions to an equation
Yeah.
in modular arithmetic is really tied to
Yeah.
the square structure of the number 8 itself.
It is. Yeah.
Yeah.
Okay, so what about n equals 9, where we had of 9 equals 3 based on that square root definition?
Right. So now we're solving x squared is congruent to 0 modulo 9.
Okay.
So again, we look at those possible remainders when you divide by 9.
Right.
From 0 up to 8.
Okay.
And we see that 0 squared is 0. 3 squared is 9, which is also 0 modulo 9.
Yep.
And 6 squared is 36. Again, 0 modulo 9.
Right.
So we have 3 solutions,
Uh-huh.
0, 3, and 6 modulo 9.
And again, that lines up
And
with
again,
the previous definition.
it lines up perfect.
Okay, and then finally, n equals 10, where a of 10 was 1.
Right, so for n equals 10,
Yeah.
we're trying to solve x squared congruent to 0 modulo 10.
Okay.
And if you check those remainders, 0 through 9,
Uh-huh.
you see that only 0 squared is 0 modulo 10.
Right.
So you only have one solution, x equals 0 modulo 10.
And again, that matches
consistent.
with the 1.
Yeah, it's pretty amazing how these different perspectives all come together.
It is, yeah. Okay, so now for that third definition, right?
Yeah.
Max sub d divides n of GCD bevel n over d.
Okay.
And let's break that down a little bit.
Yeah.
So we know GCD, that stands for greatest common divisor,
Yeah, the biggest number.
the largest number.
The largest positive integer that divides 2 or more integers.
Right, without a remainder.
Without leaving a remainder, exactly.
Okay.
And in this definition, what we're doing is we're looking at every divisor d of our number n.
Mm-hmm.
Okay?
Okay.
And for each of those divisors, we calculate the greatest common divisor between that divisor and n divided by that divisor. And then a of n, the value in our sequence, is the biggest of all of those greatest common divisors.
Okay, that one sounds like it's a little more involved to actually calculate.
Yeah, it's a little more hands-on.
So can we do an example, maybe like n equals 12?
Sure, yeah.
So according to that second definition, the largest square that divides 12 is 4, and the square root of that is 2.
Right.
So a of 12 should be 2.
Yeah.
So let's see if this third definition actually gives us the same thing.
Okay, yeah, let's try it.
Okay.
So the divisors of 12 are 1, 2, 3, 4, 6, and 12.
Right.
All right, so let's go through each of those
Okay.
and calculate the GCD of d and 12 over d.
Okay.
So GCD of 1 and 12 over 1, well, that's just GCD of 1 and 12, which is 1. GCD of 2 and 12 over 2, that's GCD of 2 and 6, which is 2.
Okay.
GCD of 3 and 12 over 3, that's 3 and 4. GCD is 1.
Yeah.
GCD for 4 and 3, again, 1. GCD of 6 and 2, that's 2.
Yeah.
And finally, GCD of 12 and 1 is 1.
Right.
So the biggest value we got there
Yeah.
was 2, which is exactly what we expected. Because a 12 from the second definition was also 2.
Right. It's amazing how they all line up.
It is. Yeah, it's really quite elegant.
It is. So the OEIS mentions that proof, that equivalence between those definitions 2 and 3,
Right.
relies on this concept of the square free part of n.
Yeah.
Can you explain what that is?
Sure. So every integer that's bigger than 1, we can factor it into a product of primes, right? And those primes have exponents.
Yeah.
And the square free part of that integer is basically what you get when you just take all the distinct prime factors, but you raise each of them to the power of 1.
Okay.
You're kind of stripping away any square factors.
Right.
So, for example, 12, right? That's 2 squared times 3 to the 1.
Yeah.
So the square free part of 12 would just be 2 times 3, which is 6.
Okay.
And Elmer's proof is really clever, right? It shows how that maximum GCD of d and n over d, it really isolates that square part of the prime factorization. And the square root of that is exactly that b we were talking about earlier.
All right.
Where n is b squared times c, and c is the square free part.
Okay, that makes sense.
Yeah.
So the OEIS also talks about this idea of the inner square root,
Yeah.
where the square root of n can be written as b times the square root of c, and b there is our A000188 of n, and c is A00007913 of n, which is that square free part.
Exactly.
And then they even mention A019554 of n as the outer square root, which is just b times c.
Yeah.
So it's interesting how this sequence gives us this way to kind of decompose the square root of any number.
Yeah, it's about separating out the rational part of the square root, which is b, from the irrational part, which is the square root of c, after you've removed all those perfect squares from the integer n.
Okay, so let's shift gears a little bit and talk about some formulas.
Okay.
So the OEIS gives this really cool multiplicative property.
Yeah.
It says that a of p to the e is equal to p raised to the power of the floor of e over 2.
Where p is a prime number,
right,
and e is a positive integer.
Right.
So that seems like a really powerful tool for calculation.
It is. It's really handy.
Yeah.
So a sequence is called multiplicative if a of m times n equals a of m times a of n.
Okay.
Whenever m and n are relatively prime, meaning they don't share any common factors other than 1.
Right.
And this property is really helpful because it lets you break down the calculation based on the prime factorization.
Yeah.
So for this particular sequence, if you take p equals 2 and e equals 3, we're looking at a def of 8.
Right.
the floor of 3 over 2 is 1.
Yeah.
So a DAF of 2 cubed is 2 to the power of 1, which is 2.
Which is what we got before.
Exactly what we found before.
Right.
And we want to do something a little more complicated, like a thorough of 36.
Okay.
36 is 2 squared times 3 squared.
Yeah.
And 2 and 3 are prime, so we can use the multiplicative property to say that a of 36 is of 2 squared times of 3 squared,
Okay.
which is 2 to the floor of 2 over 2, times 3 to the floor of 2 over 2.
Uh-huh.
So that's 2 to the 1 times 3 to the 1.
Which is 6.
Which is 6, and we can check that, right?
Yeah.
The largest square that divides 36 is 36,
Yeah.
and the square root of 36 is indeed 6.
So it works.
Yeah.
Okay, cool. So that multiplicative property definitely simplifies things.
Yeah, for sure.
Another formula that's given is A of n equals the sum over all d squared that divide n of d,
Right.
where Benner is Euler's totient function.
Yeah, Euler's totient function, that's A000000.
Oh, right.
And that counts the number of positive integers less than or equal to d that are relatively prime to d.
Right.
So it's pretty amazing that that pops up here.
It is. Yeah, it seems like this sequence is related to so many different things.
Yeah, and this formula really shows that, right? It connects the square divisors of a number to the count of numbers that are relatively prime to those divisors.
Yeah.
So again, it's just another example of how everything in number theory
It's all connected, is connected in a way that you might not expect.
Yeah. So for those out there who are, into the more advanced stuff,
Yep.
the OEIS also gives the Dirichlet series
Oh, yeah.
for the sequence.
The Dirichlet series.
So that's the sum of n over n to the s for n greater than or equal to 1
Okay.
equals zeta of 2's minus 1 times zeta of s divided by zeta of 2's
Right.
for the real part of s greater than 1.
Yep.
And that might be a little bit advanced for some people who are just getting into number theory.
Yeah, it's definitely getting into the realm of analytic number theory.
But it shows how much analysis has been done on this.
Yeah, the Dirichlet series is a powerful tool for understanding how arithmetic functions behave on average.
Yeah.
And this particular Dirichlet series connects it to the Riemann zeta function.
Right.
Which is like the holy grail of number theory.
Right. So speaking of average behavior,
Yeah.
Finch and Seebaugh found that the average order of n is approximately 3 log n over pi squared.
Right, which means that on average, the inner square root
Yeah.
grows logarithmically with n,
Okay.
with that constant factor determined by pi.
And there's also a very straightforward formula. A of n equals the square root of n over A007913 of n,
Right.
where A007913 of n is, again, the square free part of n.
Exact.
So that seems like a really efficient way to calculate it if you know that square free part.
It is, yeah. You just divide n by its square free part,
Yeah.
which isolates that perfect square factor,
Huh?
and then take the square root and you're done.
Perfect. And what else do we have here? Oh, yeah. So the OVIS mentions this recurrence relation that was observed by Velenyanev
Uh-huh.
and then clarified by Antti-Karttunen.
Yeah.
It says A of 2n equals A of n times A096268 of n minus 1 plus 1.
Right.
And there's a condition there based on the 2-adic valuation of n.
Right.
And for those who don't know, the 2-adic valuation of n, that's just the exponent of the highest power of 2 that divides n.
Yeah, it's basically how many times you can divide n by 2 before you get an odd number.
Right.
And this recurrence relation shows that there's still a lot to explore with this sequence,
Yeah.
because it ties how the sequence changes when you multiply by 2 to the power of 2 in its prime factorization.
Right.
So there's some deeper patterns there.
Okay, cool.
Yeah.
And for people who like generating functions, Ilya Gutkovsky gave one for this
Really?
sequence.
Yeah.
And it involves Euler's totient function again.
It does. It does. It's amazing how that phi of k keeps popping up.
It really is, yeah.
And generating functions are just another way to represent a sequence.
Yeah.
And they can reveal some cool stuff about the sequence.
It's like combinatorial insights or algebraic insights.
Exactly.
Yeah. And finally, the OEIS is really good about pointing to related sequences.
All right.
So for this one, we see links to A019554, which is that outer square root,
Right.
and A00008833, which is n divided by the square free part of n,
Right.
which is the largest square dividing n. So all these connections are they're super helpful for studying this stuff.
Yeah, the OEIS is like this amazing network
Right.
of mathematical ideas, and following these links can really help you understand
Yeah.
how it all fits together.
Okay, so to recap our exploration of A000188, we saw how this sequence defined in these really different ways.
Yeah.
through those solutions to quadratic congruences,
Yeah.
that square root of the largest square factor,
Uh,
and the maximum of those GCDs, of the divisors,
yeah,
they all lead to the same set of number.
they do, which is just mind-blowing.
It's really cool.
It really is.
And it just highlights how connected everything is in number theory.
Exactly. And it's not just some isolated thing, right? This sequence connects to all these fundamental ideas.
Right.
Like square-free numbers, Euler's totient function,
Multiplicative properties.
multiplicative properties, Dirichlet series,
Recurrence formations.
recurrence relations, generating functions.
And the list goes on.
Yeah. And the fact that multiple mathematicians came up with those different definitions
And proved they were all the same.
independently, right?
Independently, yeah.
It just shows how strong
Yeah.
those mathematical relationships are.
And it makes you think, right? If we can define this inner square root and connect it to the properties of squares,
Yeah.
are there like similar concepts for higher powers?
That's a great question.
Like, are there sequences that talk about the inner cube root
Yeah.
or the inner fourth root of an integer?
Yeah. And you know what? The OEIS actually has sequences that do explore those very ideas.
Wow.
So, for example, A0053-150 and A0053-164,
Okay.
they deal with aspects of cube roots of integers.
That's really cool.
So it's really suggesting that those principles we talked about for squares,
yeah.
they have natural extensions to higher powers.
And it just opens up this whole new world.
It does. It does. It's an invitation to explore.
So for all the number theory students out there,
Yeah.
I really encourage you to check out the OEIS.
It's a treasure trove.
Explore A000188.
Yeah, and follow those links.
Follow the links, follow the formulas.
Yeah.
It's amazing to see how these simple ideas can lead to this whole web of mathematical connections.
Absolutely. It's a beautiful thing.
Well, thank you for joining us for this deep dive into the OEIS.
My pleasure. It was great to be here.